let's talk about how we describe, we've done bar charts for energy. We can also do bar charts for momentum, okay? And so really what we're doing is we're writing this out as, here's our initial momentum, here's our impulse, we're adding them together. You can see this is just changing around the equation for impulse momentum theory because this is usually P final minus P initial, so we're just moving it over here. So we have our initial momentum, our impulse, we draw it in a different color, and here's our final momentum, okay? So we can draw this out so we can visualize what's happening in terms of the momentum. So we're gonna try this out. We're gonna draw bar charts for the following three situations, and I'd like, let's say this is positive, negative, so here's our line. Very bad. Wow, I wish I could draw a straight line better. Let's try these. Okay, so remember, this is going to be initial, J, final, okay? So we'll start, we'll do it like this. So what's our initial momentum? And let's do this, we'll just do this 3 times. Yeah, so for all of them, the initial momentum should be the same, okay? So it's just gonna look like this. Right? And why is it the same?
It's all the same initial conditions.
Yeah, same initial conditions, same tennis ball, hit with the same speed, okay? For part A, this is A, B, C. Let's say it hits the net and stops. So what does that mean about your final momentum? 0, right? It has to be 0, so we'll just put that there, okay? What about the impulse? Has to be negative because these two things have to add up to equal 0, okay? So here we have a positive initial momentum, we have a negative impulse, they cancel out, you get 0, okay? In the second situation, the ball hits the net and bounces back towards the server, so what's our final momentum gonna look like? Slightly negative, right? So a little bit negative. How do we get that from impulse? Positive or negative impulse? Negative, but is it gonna be bigger or smaller than the previous one?
Smaller.
Doesn't have to be bigger, it has bigger change.
Bigger because you have to end up with something negative, right? So this and this have to be the same size as this, okay? Oh, smaller, you mean more negative?
Yeah.
Okay, well, in that case, yes.
Small and negative.
Last but not least, we end up with something that keeps traveling in the positive direction. So what does the final momentum look like?
Slightly lower than the initial.
It's positive but smaller than the initial. What does that mean about our impulse?
Just slightly negative.
It should just be slightly negative because it's just taking a little bit of a chunk off of your initial momentum, okay? So those are these are ugly, I'm sorry, but those are our momentum impulse bar charts, and it's a good way of thinking about what's happening and visualizing it in terms of conservation momentum. We've been talking about momentum and impulse and how they're related. Impulse gives you a change in momentum. Impulse is a force applied to something over time. It doesn't have to be a constant force. It's just the integral of the area under the force curve. So we have a way of expressing this, which is these momentum bar charts, where this is your initial momentum, then you add the impulse, we make it a different color so that you can tell it's something else, and then you have your final momentum, okay? So this would be like, if we're talking about the tennis ball situation, what would this be like? Actually, that's kind of a weird example. But yeah, let's think about that. So you start with a particular momentum. Let's say this thing's moving forward. How do we know it's moving forward?
Positive.
It's positive, what's on the positive side, okay? Then we add an impulse in the same direction. So what would that be like?
That'd be like it hitting something on the way.
It's sort of be like you hitting it, like if you hit it and then you hit it again, right? So if it's already moving forward, you hit the ball again, and then it moves faster but in the same direction, okay? Tennis not the best example for this. Maybe if it's like if you're skateboarding and someone gives you a push, right? Then you would start with this speed and go to a higher speed, okay? Remember, if you have a negative impulse, it'll make this one smaller than this. If it's large enough negative, it'll end up you can actually turn something around. So that's how these bar charts work, just as a reminder. So now I'd like you guys to rank the impulses from largest to smallest on an egg, okay? And there's 3 situations, so make sure you rank the impulses for the egg. Awfully quiet in the chat here. Okay. Let's see. We're mostly thinking it's C. Please discuss. We'll vote again.
You pick C?
Hey, yeah, it's C. So, what's our initial momentum? Okay, well, what's our final momentum? 0, right? So the impulse, they all start with the same initial momentum, okay? It's just whatever the speed is before the egg hits the floor. And then that's gonna have to be exactly equal to the impulse. If they all start with the same momentum, that means they all have the same impulse. And that's because we know that it has to stop when it hits the ground, regardless of how squishy the ground is, okay? Slight caveat to this. What does it look like when an egg breaks?
Yep.
Yeah. So that actually does count as a change. It's in the X direction. There's definitely like a different situation happening when it explodes. And you can actually measure how far the egg explodes and like figure out the speed it had to be going to shoot stuff in that direction. So you could potentially get a little bit of a different answer if the egg breaks. But for our purposes, to the what we would call like the 0th order approximation, so without going into a lot of detail, this is still the right answer, okay? But I just want to prepare you for later. We're gonna talk about explosions, and you can actually, even though like the net momentum of something is 0, you can still, if things break into pieces, they all have momentum too. So that's a separate conservation momentum issue. As long as you're just saying, we're not talking about the egg breaking, you're just saying it starts with they all start with a particular speed and they all stop, impulse should be the same, okay? So, remember, bringing an object to rest requires a certain amount of impulse, but what we are not talking about in this previous problem is that all of those situations use the same amount of impulse, but what was different about them? Remember, what's impulse made up of? What are the 2 variables that go into impulse? How do you calculate impulse?
It's like PI, the initial.
Well, no, so remember when we calculate impulse, we're taking an integral of a force curve, right? So we're worried about force. What's the other variable?
Delta T?
Delta T, yes, time. So force and time, okay? So if you have the same impulse, you can still adjust force and time, all right? So if you have a longer time, what does that tell you about your force? Yeah, smaller, right? So if you have the same impulse, you make the time longer and the force smaller. So remember, if you increase the time over which an impulse is delivered, this decreases the average force, which if you're an egg or a person in a car crash, for instance, the average force matters a lot to you because the average force being lower means you get less exploded, which is usually a life goal if you want to be alive, okay? So remember, no matter what, your initial momentum counts. Your impulse, if you come to a stop, your impulse has to be exactly equal to your initial momentum, right? And that means that whatever you start with, you have to dissipate that. But how you do it will matter, okay? So, and yeah, just remembering that this average force and time are what make up the impulse, okay? So here's a question about this. So, remember, anytime you get in a car accident, you have to spend a lot of money making your car not look like it was smashed, okay? So let's say we build cars out of hard rubber material so they just bounce off of each other and don't damage the car. Is this a good idea? Why or why not? And I want you guys to discuss this for about a minute, but use physics words like impulse, momentum, force, time, okay? Not like regular English words.
If you think about it, bro, you can't make your head.
So it's just gonna make your like you can't really say center of gravity, so that would be low point. But in the front it's gonna be really fronted. So you ram into something in the front and then your front end, yeah, it'll like fold in and then there's something hard right behind it, so it's gonna push into the next car.
So I'm thinking any engineer, if you get your drive like if our
Yeah, they go fast.
The go-karts don't go
They
60
have
miles.
crumple.
Someone goes 60.
Whenever you see like if you go in like
No, they
or something like that, and there's like
Yeah, they do.
a
Have you ever
which
been
looks
there?
like in the middle, that's where it's
You have to
supposed
wear like a helmet, just sign like a little wave.
is that to help?
Well, yeah, because you could do
Yeah, 'cause
damage,
Yeah.
because you're not supposed
more
to do
force,
that.
because
So why do you think that's not a good idea? I think it's okay, I think it's kind of funny,
Because you're going that way, you have like a really big force and you're
it's
going
the same
that way.
force, which makes it so that it's
Yeah, so like if you bounce off each other, then it's like, I don't know, you could like
so you shouldn't
flip
do it off of rubber
something.
because it's just gonna fold
Really
and
bad
then you're
bounce
gonna just
off.
hit something harder and it's gonna go.
Terrible idea.
I agree. You go like, I don't know.
So you think
all the energy
because
gets absorbed
It'd be fun and be like, oh,
if they bounced off each other. It's like when you're going paintball, as you can see. It's like when you shot at paintball, paintball doesn't explode, but it's also exploding when you
In that,
if you had
you just like
panels around the
crunch together.
Yes,
It's gonna be like
you want the squish, the crumple zone is for a reason, yes. Okay. Alright, so anybody want to explain why this is a terrible, terrible idea, but using physics words like impulse and momentum?
Is this more max?
No. We could just sit here in awkward silence for a while. That could be fun too. Yeah? Alright. Okay.
Would the impulse of the car have more time, so it'd be less force, but then the impulse that affects the person would be more force and less time?
Yeah, you're in the right direction. So remember when we talked about bouncing versus stopping, right? So if this ball just stops, what does the impulse look like? Well, you have just this initial momentum and then the impulse is equal to the initial momentum. But if it bounces, right, the impulse, when we did those bar charts, if something bounces, the impulse is much higher. So when the impulse is what's limiting the force, that you can distribute the force and time differently, but you have more of both if your impulse is bigger. So ideally you want the impulse to be as small as possible. The smallest possible impulse you can get in a collision is if it stops. Right? Or if it keeps going, but in a car accident that's not really necessarily an option. So if something bounces back, you're going to inherently have more impulse and therefore more force and over time. Okay? So I think what you're talking about is what we're going to talk about next, which is that if you have to get in a car crash, how do you want the force distributed and how do you make sure the time that before you have like a hard impact is longer? And that there's a short answer to that, and what is it?
Airbags.
Airbags, right? Because if you just hit your face on the steering wheel, that's a short time interval but a large force on your face, which is bad for your face, okay? If you hit the airbag, really all it does is, like, let's say your face is traveling from here to the steering wheel, it slows down the amount of time and cushions the impact, which means that the overall force you experience is going to be lower, okay? But because it takes longer to have that impact. The other thing you want to think about is when you have a collision, cars are actually designed to get destroyed in accidents because you have a lot of energy that you're trying to dissipate, not into you. So the worse the car looks, usually the better off you will be, right? So cars are actually designed to get crumpled and destroyed, and strategically too. Actually, there's when I was in Europe, people drove Fiats before they were here, and they're really small, and they had an engine in the back, so that they said like the crumple zone of a Mercedes and a Fiat both ends after the engine, which means that the front of the Mercedes would be crushed, but the entire Fiat would. Sorry. It's also a joke that was told to me in Polish. So, but I feel like it translates a little bit. Anyway, we've gotten off topic. The crumple zone is supposed to dissipate all that energy so that it doesn't hurt you, okay? So, yes, let's try another clicker question. think we're feeling pretty good about D. We won't vote again on this one. The answer is D, okay? And this is what we just talked about, right? If you bounce, if you change directions, that requires more force than stopping, okay? Which means you have a larger impulse, which means that then it means that you have a larger impulse, which was the question. Okay, I got tangled up in that one. Cool.